Hello everyone, welcome to another class of our course, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are currently in the week number 5, so as always, let's first recap what we have done so far. So we started by presenting the architecture of a single artificial neuron, which had two inputs, and then we generalized this case to get an equation for a neuron with an arbitrary number of inputs, which is shown in the bottom formula. And on the coding side, we'll learn how to classify points belonging to different classes from each other. So for this particular arrangement of data points, we demonstrated what would be the limitations of using a single artificial neuron for classification. As you can see, a single neuron does not have enough capacity to address more complicated arrangements of points. In this case, the points 4 and 5 will be incorrectly classified. And if we change the boundary in the following way, well, now the points 6 and 9 will be misclassified. Well, if our data is clearly separable by a line, then maybe we can get away by using a single artificial neuron. But let me tell you, in a real-world scenario, this is not going to be the case. Data will not be clearly separable by a line. So we need to improve this. To increase the capacity of our model, we introduced a network of artificial neurons. In the simplest case, a network has 3 layers: an input layer, an output layer, and a hidden layer. Hidden in this case only means not being an input layer and not being an output layer. And now it's a good time to mention one very trendy and hyped term in machine learning. And this term is deep learning. So what does deep learning mean? Well, this term merely means using neural networks that have multiple hidden layers. Here we have only a single hidden layer, so technically we are still not doing deep learning. But if our network had, for example, 5 hidden layers, then we can refer it as a deep neural network. And then another important thing to consider is what kind of neurons do we have here? Well, in the input layer, we have our data points. So they are the simplest possible neurons that we can have, which have only outputs. In this case, in the output layer, we have a neuron which does not have an activation function. Yeah? But in the hidden layer, we have 2 fully fledged neurons which have activation function, and the activation function is a sigmoid function. So far, we have been illustrating our artificial neurons and our networks as circuits, and I think this is a very good starting point to fully grasp what is going on. But once we get more comfortable with them, we can start using different visualizations like the one on the right. So this is a more common way to visualize neural networks. You can only see that neurons are connected to each other, but you do not explicitly see all the connections. As you have already experienced, the biggest challenge in implementing neural networks by ourselves is to compute the backward pass. So what is a backward pass? To remind you, a forward pass would be when we start from our data points, from initializing our weights and biases, and then we go from left to right and compute the final output of the network for this data point. Yeah? Then a backward pass would be when we start with the output, we have the output, and then we need to compute partial derivatives of this output in terms of all the weights and biases. So to compute the backward pass in this particular case, we need to compute partial derivatives in terms of 9 variables, so from A1 to C3. And we did this last time, so there is no point in repeating the procedure. What we have learned is that we should always start from the end, because if we start from the end, we can capture certain terms that are repeating throughout the network, and then we can reuse them. Well, in this case, 2 essential steps are computing the partial derivatives of the output in terms of Z1 and Z2. These are 2 sums. So if you have these terms, then calculating the partials of the weights and biases becomes a very trivial task to do. And this is where we ended the class last time. So I ask you, what is the problem with this optimization strategy that we have been using since the beginning? So the main problem is that we cannot address the magnitude of the mismatch between the output of the network and the label of the data point. So we need an objective measure of how good or how bad our network is performing. And a function that would give us such an objective measure has a couple of names. So we can call it an objective function, we can call it a cost function, or we can call it a loss function. So these are the 3 most common terms. Now let's see how we can implement such a function. This time, since we are focused on a loss function, I want to go a little bit deeper into the topic. Not because I want to make machine learning experts out of you, but because usually how this is handled is you have a certain problem, and it's a recognized problem. It's similar to other problems that other researchers are dealing with. And then you are simply given a recipe. Yeah, if this is your problem, you should use this loss function. If this is your problem, use this loss function. And not many people know what is actually going on. So what I want to achieve here is give you a little glimpse of what is actually going there behind the scenes, just for you to have an idea what kind of processes are happening and what are the limitations and what are the challenges. So here we have a single neuron and we have a data set with 6 points. Only this time our labels are expressed as text, as strings of text. So we have blue points and we have red points. Yeah. So what can we do here? So let's try to first formalize what would be a cost or loss of a single data point here. Yeah. So let's start, for example, with the first data point. And this data point has x coordinate 0. Well, we can plug this x coordinate in the appropriate outlet in the network. Then the y coordinate will be 0.7. We can plug it in the appropriate outlet in our neuron. And the label will be a string, blue. So now let's say that we initialize our weights and biases with some random numbers. And when we multiply and add everything, we get the output 0.63. So a loss or a cost function would then compare this output of the neuron with what would be our desired output. So what is our desired output? Well, our desired output is defined by the label of our data point. So in our case, the label for this data point is blue. So we want our network to output blue when it sees these coordinates, yeah? But how can the neuron output the string blue? Well, it cannot, because our neuron can only output real numbers, and such number is this output, 0.63, yeah? So now we come to a very important idea in computation, which is that of encoding. So what we need to do is we need somehow to encode these labels, yeah, so that we can compare them with the network's output. This means we need to encode the meaning that we give to our data points to some kind of a number. Well, how can we do this? Well, the meaning that we give to our points is that they are red points and that they are blue points, yeah? And a blue point is something different than a red point. So if we use numbers to encode this meaning, this means that we somehow need to maintain this distinction between red and blue. So we need to use two numbers that would be different from each other. Because if we use the same number, for example, 0 for blue points and for red points, then there is no difference between blue and red. If we want to still distinguish between blue and red, we need to use two different numbers. So what we did so far is we, in the last example, encoded blue as +1. And we encoded red as -1. Yeah? So this is a valid choice. And let's, just for a moment, stick with this encoding, just to see where does it lead us. Here, I added another column to our data points, which also contains the numerical labels. And now let's see if now we can formalize some kind of a loss or cost for a single data point. Again, we choose the first data point, which is 0 and 0.7. We plug 0 in the appropriate outlet, we plug 0.7 in the appropriate outlet, and now we have the label, which is +1. Again, we initialize our weights and biases to be some random numbers. When we multiply and add everything, we get the output 0.63. And now the loss or a cost function would compare this output with our desired output. So what is our desired output now? Well, our desired output is now a number, which is +1. And our output also produces a number, which is 0.63. So now these two things are comparable to each other. They're both numbers. So what do we actually want from our neuron? Well, we want our neuron to match the label. Yeah. So for it to be a correct prediction, we want the output to be the same as label. So we want the output to be 1. Yeah. And how can we then address the mismatch between what we have and what we want? We can, for example, subtract the output of the network from the label. So what we get is 1 minus 0.63, which is a number 0.37. 0.37 shows a mismatch between what we want to have and what we have. And in machine learning, we call this value a loss or a cost for our chosen data point. Okay, let's say that we now have again updated the weights and biases, and we are still considering the same data point. So if we did not change the input, and we change the weights and biases, what else will change here? Well, what will change is output. So let's say that now we get the output of the network to be 0.87. What is the loss now? Well, the loss will be 1, which is the label, minus 0.87, which is the output, equals 0.13. Yeah? So loss used to be 0.37 and now is 0.13. So we can agree that this loss became smaller, no? Well, if the loss goes down, is our neural network actually performing better or worse? Well, it is performing better because 0.87 is closer to 1 than the previous number. Yeah. So the lower the loss we have, the better the prediction we get. Okay, so now let's say that we again updated our weights and biases, and we are still with the same data point. Now we get the output 1,11. What would be the loss now? Well, it would be 1 minus 1,11 is negative 0.11. We have a negative loss. So that sounds a little bit funny, no? Well, never mind. Let's go to the next slide. Now, let's just display the loss from the last 3 slides. So the loss used to be 0.37, and it became 0.13, and finally, it is negative 0.11. So can we agree here that our loss got progressively smaller? Well, if the loss got progressively smaller, then this should mean that our prediction got progressively better, no? So what is then the goal of our neural network in terms of the loss? Well, its whole purpose would be to minimize this loss between what we get and what we need. And how can we actually minimize the loss? Well, by using calculus, by computing partial derivatives. Now, before we start implementing the loss function, let's see how we can improve this measurement of error or mismatch a little bit. So what we showed so far is that to compute the cost for any data point, we need to subtract the output of the network from the label. Well, the problem is if we do just that, we sometimes get a positive error and sometimes we get a negative error. And I'm sure you agree that it would be better if our error will always be a positive number. Well, how can we address this? Well, we can, for example, compute the absolute value of this expression, label minus output. So here is the formula that we actually applied. But there is actually a better way to do this. So instead of finding the absolute value of the expression label minus output, we could instead square this expression. As you already know, squaring any number will make it positive. So negative 2 times negative 2 will give you positive 4. So let's just compute the mean squared error. So in the first case, we get that the error is 0.13. In the second case, 0.0169. And in the third case, 0.0121. So what you might be asking me is, what is then the difference if we take the absolute value of this expression or if we square this expression? How do the outputs differ from each other? Well, let's take a look. Here I created 2 tables. So on the left table, the right column shows label minus output. And on the right side, we have the right column showing label minus output squared. And the middle column is the same for both cases. Yeah, it has values varying from 1 to 0 in the decrements of 0.1. So how can we describe, what do we see? How do these outputs differ? Yeah. Well, let's see what happens at the both ends of the spectrum. So you see, when the output is very close to the label, for example, when the output on the left side is 0.9, then the measure of the loss is 0.1, which is 10% loss. Yeah. If you look at the right side, for the same output, the error would be only 0.01, so 1%. So what does this tell us? Well, if the output is close to the label, the mean squared error will make this less of an actual error, while the absolute value will give us that this is still a significant error. And now let's look at the last rows on both sides. If the output is very far from the label, for example 0.1, then both loss functions, one with the absolute value and one with squaring the expression, will have relatively similar values. Yeah. So on the left we will have label minus output is 0.9, and on the right we will have label minus output squared is equal to 0.81. So they are relatively similar. Yeah. So when our outputs gets closer to the label, then our mean squared error actually becomes less sensitive to the error. So it shows less error. So let's go back to our formula for computing mean squared error. So we have the term Cx. This term simply means the cost for a single data point x, and x is here a variable, means any data point. And by using this formula, we can compute the forward pass. When we calculate the final output of our neural network, then we subtract this value from the label, and then we square this difference. This is how we end the forward pass. And after that comes the backward pass. And now we start from the end, which is the cost of a single data point, and we need to compute the gradient again in terms of all weights and biases. So what is the only thing that we are actually missing to do that? Well, we need to be able to calculate the derivative of the cost function in terms of the output of the network. and this would be dcx over dA. So what is this derivative equal to? Of course, we can use algebra to compute this derivative, but we can also use our circuit diagrams to do it. So let's just do that instead. So the formula is c of x equals label minus the output squared, and we are interested in finding delta cx in terms of the output A. So let's see what elements we have in our circuit. Well, we have label, then we have the output A, and we want to subtract A from the label. So we want to have positive label, but the negative output. So how can we do this? Well, for example, we can multiply A by -1 to get minus A. So then -1 would be one element here. So what do we do next? So if we multiply A with -1, we will get -A. And the label is positive. So label minus A is the same as adding these two outlets. So if we add label to this value, which I call A star, label plus A star is the same as label minus A. Now, what I need to do is now I need to square this sum. So how do I do that? As you already know, squaring something is the same as multiplying it by itself twice. So let's do that. Let's move this a little bit here, copy it, and paste it. And now we have the same diagram twice with exactly the same elements. Okay, so what we can do now is we can actually multiply these two things. So we have multiplication, and then we get the cost for a single example. Now we can ask, what is the derivative of the total cost in terms of our output? And the output is here, but also here. Yeah. So as you can see, there is some kind of branching going on because each of our elements shows twice, so it branches. So let's see how we can deal with this. So we need to compute this partial derivative here. Yeah. And how can we do it? Well, we can do it by using the chain rule. So to compute the partial derivative of the total cost in terms of A, we need to mark some additional elements. I will call this element here P1, I will call this element P2. So to compute this partial derivative, we need to compute the partial derivative of the total cost in terms of P1, and then P1 in terms of A star, and A star in terms of A. But there is another path that we need to consider. So this is the partial derivative of the total cost in terms of P2, P2 in terms of A star, and then again A star in terms of A. So let's write this down. So delta Cx in terms of delta A equals delta Cx in terms of P1 times delta P1 in terms of delta A star times delta A star in terms of delta A. But then there is another path that we need to consider, so we need to add that path too. So plus delta Cx over delta P2 times delta P2 in terms of delta A star times delta A star in terms of delta A. Okay, this looks like a complicated expression, but trust me, it is very simple. So what would be the delta Cx in terms of delta P1? Well, this is just a multiplication circuit, so we know that the output will be the other element, so P2. So this will be equal to P2. Then, what is delta P1 in terms of delta AX? So this is this one in terms of this one. Well, as you can see, this is a simple addition, so the partial derivative will be equal to 1. So this is times 1. And then what is delta AX in terms of delta A? Well, this is again just a multiplication, and as we know, the partial derivative of A star in terms of A will be the other element, which is -1. So times -1. Now we have plus. And now again, what is the derivative of Cx in terms of P2? Well, it will be P1, just the other element. What is the P2 in terms of A star? It is again equal to 1. And what is A star in terms of A? Well, it is again -1. So what we get is negative P1, negative P2. And what are P1 and P2? Well, P1 is label plus a star, and p2 is also label plus a star. So this means that these two elements are exactly the same. So this is equal to negative 2 p1 or p2. Yeah, it doesn't matter. And what is this equal to? Well, this is equal to negative 2 times label plus a star. And what is this equal to? Well, a star is just negative a, so we can say that this is just equal to negative 2 times label minus a. And this is the value of our partial derivative. So as we computed it, the partial derivative of the total cost in terms of the output of our neural network is negative 2 times label minus a. Is this the only formula that we can use? Well, it is not. Sometimes you will see another formula, which will be this. So if we started defining our mean squared error as not label minus the output, but as output minus label squared, then the partial derivative would be somewhat different. The partial derivative would be 2 times output minus label. Well, our case and this case is not really different, because 2 times a minus label is the same as negative 2 times label minus a. So you can use whichever you want. Let's now try to visualize what we get when we attach a cost function to our neuron. Well, we add it to the right of the output, yeah? So when we add it, this looks like I added an additional layer to our network. And now the final output is actually C. So the only thing that we need to know to implement this function in code is the derivative of the final output C in terms of the network's output, which is just output, yeah? And we know that the partial derivative is equal to negative 2 times label minus s, or 2 times s minus label. And now let's do an exercise where we implement this in Python. So let's start with the exercise number 7, which is implementing a cost function for classification with a single neuron. Well, let's first run the code that we are given. So we are just given this standard initialization code, and we are given a function plots data. Yeah? We are given some data and some labels here, and we can use the function plot data to see actually how our distribution of points looks like. So this is the same as last time. We have 3 red points and we have 3 blue points. Okay, what is the task? Well, the first task is to implement the following neural network architecture and minimize the cost for a single data point. Okay, so we start with a single data point. How do we do that? Well, since data is all of our points, we can just say data index 0, which will give me the first data point, yeah? If I want the label for this point, I will just say labels of the index 0, and I will get the appropriate label. So what I can do then, I can unpack this data into x and y coordinates. So I can say x, y equals data, and I can say current label equals labels of 0. Yeah. So now we have x and y and our current label. The next thing I need to do is I need to initialize these two weights and this bias. So how do I do that? So we can use the function mp.random.normal, and we say size equals 3. This will give us 3 normally distributed random points. Or I can use the function mp.random.randn, and then just pass the parameter 3, which will give us again 3 normally distributed random points. So now I can say, since I have 3 values here, I can unpack them to w1, w2, b is equal to this. Yeah. So if I now say w1, w2, b, I will get 3 normally distributed random values. So the next thing I need to do is I need to compute the output of this function. So what would the output be? So the output, I will call it O, would be equal to, O is equal to w1 times x plus w2 times y plus b. If I say O here, this will give us what is the value of the output. So now that I have the output, I need to compute the cost for this data point, yeah, in order to finish the forward pass. So I will write C, which is cost, equals to label, and our label is the current label, yeah, current label minus the output squared. So how do I type squared in Python? I just do this multiplication sign twice, and this will square this current label minus output. Let's plot it. we get that the cost for this example is 8.704. So it's relatively high cost. Why? Because our label is 1, but the output of our network is negative 1.95. So therefore, this value is not so small. Now we are finished with the forward pass and we go to the backward pass. What do I need to do? I need to compute the derivative of the total cost in terms of the output. Yeah. So what is then dc over d output? I will call it d output. So I will write do, which means derivative of the cost in terms of the output. Yeah. This will be equal to negative 2 times current label minus output. What is this equal to? Well, it is negative 5,9008. Okay, what else is there? Well, we need to compute the partial derivative of the cost in terms of W1, W2, and B. Okay, what is this going to be equal to? Well, it's just going to be the cost over D output times D output over DW1, D output over DW2, and D output over DB. So if I write DW1, DW2, DB, this is just going to be, in all three cases, the O times, what is the derivative of the output in terms of W1? Well, it's just X. What is the derivative of the output in terms of W2? Well, it's just Y. So DO times Y, what is the derivative of the output in terms of B? Well, it's just 1. So DO times 1, or just DO. Yeah. Now we have computed the partial derivatives. What would be the next step? Well, the next step would be just to update the values of W1, W2, and B. So we need to minimize this cost. Yeah. So how do we minimize the cost? I will remind you this formula. So the formula is x new equals x old minus, if we want to minimize, and we now want to minimize this distance, minus derivative of y in terms of x times some small number, which we'll call step size. So let's initialize the step size first. I'll write it here. Step size equals 0.01, for example. All right. And now let's see what would be. Now let's see how we can update the values for weights and biases. So W1 will be W1 minus the derivative of W1 times step size. W2 will be W2 minus derivative of W2 times step size, and B equals B minus derivative of B times step size. Okay, now we updated the values. Let's see what would be the output now and the cost now. So if I copy this, I get the output and I get the cost. And now let's just print them, O, C. So you can see now the output is negative 1.86 and the cost is 8.19. Yeah, so the cost used to be 8.704 and now the cost is 8.193. So the cost got less. So now let's put this into a kind of working algorithm. Let's see how far we can minimize this value. Let's see how close we can make the output of our neuron to the actual label. So first we need to clean this up a little bit. So step size is fine. So first what we will do is initialize our weights and biases. Okay, so this is the first step. We initialize our X, Y, and current label. Okay, we compute the output. We compute the cost for this output and for this label. We compute the derivative of the cost in terms of the output. Now we compute the partial derivatives of the weights and biases, which all include this term here. And finally, what we do is we update our weights and biases here. Yeah. I will erase everything else. So at the end, I will now print. What should I print? Well, I can print, for example, label will be current label. Okay. Then I can print the output, which will be O. Okay, I see now the label and I see the output. And now I can print the cost, which is C. These numbers have many decimal values. I would like to round them, so I can use the numpy function round to actually round them to, for example, 4 decimal places. How I can do that? This is the variable O. I can just say np.round of this O, 4, which will round the variable O to 4 decimal places. And I want to round the cost as well. So np round cost to 4 decimal places. Now I see the label of our data point, the output of our network, and the current cost for this data point. Okay, let's see now what happens when we repeat this procedure, for example, 50 times. So let's make a loop. For I in range 50, I will just repeat this procedure. So what is going on here? As you can see, the label is 1, but the output is negative. Therefore, there is some cost for this example. And as you can see, as I go further, this cost gets less and less. Yeah. So this number is way smaller than this. And what is going with outputs as cost gets smaller? Well, as cost gets smaller, the output gets closer and closer to 1. So here it used to be negative 0.4086. And then as we lower the cost, this number gets closer and closer to 1. Yeah. Let's do it once more. As you can see now, our initial value is 1.132, so the cost is not that high, but still it goes down. Let's do more loops. So for example, 100 loops. As you can see now, cost is quite high, so the output is negative 1.07, which is far from 1, so the cost is high. And then as we lower the cost, as you can see here, when the cost is very low, then this number gets closer and closer to 1. So if we repeat it, for example, 300 times, what you will see is that we can actually get very, very close to 1. Our output can get very, very close to 1. So what we can conclude is that the mean squared error is a very efficient function for making one value approach another. So now I'd like to talk about what have we actually done with this example. So on the slide, you can see our data points. You see them plotted on a two-dimensional graph. And we see that we converted labels blue and red to +1 and -1. What can you actually display on this two-dimensional plane? So you can display data points coordinates, x and y, which then gives you a location of the point on the plane. But you can also describe data points labels. So you can make blue points and you can make red points. Yeah. So you can see the data's label on this visualization. Well, let's add another graph. This time we are adding a single number line which displays neurons output. So when we multiply and add things within our neuron, this is where the output goes. Also, what you can see on this number line is data points label. You can still make the point red or blue, even in this graph. So what we did is we actually picked the first data point, which is the point 0 here, with the coordinates 0 and 0.7. What we did next is we computed the output of the artificial neuron for these coordinates, and we got some value, which is then plotted on the lower graph. Yeah, so you can see that it's positive value. Well, what is our loss function actually keeping track of here? Well, what it is looking at is the distance between the output and the label. So we said that the label for this point is +1, and whatever our output is, there is some distance between these 2 points. So our cost function actually squares this length. And what is the actual goal of our cost function in terms of this distance? Well, its goal is to minimize this distance, to make this distance as close to 0 as possible. Yeah. So if we take the same data point and change our weights and biases, and now get another kind of output, which is now less than 1, now this will be the distance between the output and the label. Yeah, the point will be on the left side of our label, but this will be the distance. Again, we square this distance and then minimize it. The whole goal of this cost function is to minimize the distance between the output and the label. And now if we take another data point, for example, the second data point, the red point, again, when we pass this point through our artificial neuron, we get some kind of output. What we have here now is the distance between the output and its corresponding label. Well, now the label is -1 because it's a red point, so we measure the distance between this point and its appropriate label, -1. And again, we are trying to minimize this distance. So what can we then conclude about the behavior of the mean squared error? So we have a certain distribution of blue and red points, and what the mean squared error actually does is make them as close as possible to its targets, so as close as possible to -1 and to +1. So it is important to realize here that for our two labels, the output will be restricted to be either -1 or +1. Let's see this animation once again from a different standpoint. Another thing that we can observe here is that a data point can approach its target from both sides, so from left and from right. So let's just look at that. So as you can see, blue points can be on the left of the +1, or they can be on the right of +1. Nevertheless, they will still be able to approach +1 or -1. So the crucial question actually to ask here is, how do we actually decide if the output of our network matches the label? As you have seen in our example, an output can come very close to the label, but the question is, at what point do we decide that the output is actually equal to the label? Well, what we might try to do is make some kind of region around both -1 and around +1, and then say if the distance between the output and the label is less than a certain threshold, then we decide that the actual output is a blue point or a red point. So now let's try to implement using mean square error for multiple points. So let's continue with this example. So here we minimized a single data point, actually the first data point, and let's do less steps here. For example, 50. As you can see, the cost goes down. The next task is to minimize the cost for all the data points. So I will just copy paste this code here and see how I can change it. So if you want to minimize the cost for all the data points, we have a couple of choices. We can randomly choose a data point from our dataset, or we can go one by one. As we already know how to do that, let's just randomly choose the data point. If I'm interested to compute how many data points our data has, so I can say data.shape, and this will give me the shape of our data. So 6 instances with 2 elements each. Or I can also say len of data. This will give me the number of our data points. If I now want to choose a random data point, I need to generate a random number between 0 and the length of our data. So I can do that mp.random.randint. And if I now copy this expression length of data here, this will guarantee to give me a random number between 0 and length of our data. Now I can call this an index. Yeah. And now x and y values would be a data point from this index. And now current label will be labels of the same index. What is left to do is just copy these lines and replace these two lines. So now in each iteration, I'm first randomly picking an index, and I'm using this index to assign data points values and the label to our 3 variables x, y, and current label. Then I'm computing the output for this particular data point. Then I'm computing the cost for this particular data point with our current label matching the index, computing the partial derivative of the output, and finally computing the partial derivatives of our weights and biases. So let's see what happens when I run this code. Well, now the cost will not be for a single data point, it will be for all the random data points. So to make sure that you know what is going on here, I'm just going to add another line to our print. I'm just going to say data point index +1. And now, as you can see, I'm getting random values for our data points. So 4 data points second, 5th, 4th, second, and then for each of them I plot the actual label and the actual output and then the cost. So anyway, when I run this multiple times, you can see that the costs for all the data points are starting somehow to go down. Yeah, so they're relatively high in the beginning, but then as we repeat this procedure more and more times, they get less and less. Okay, now that I know that my algorithm is working, I can run it multiple times without printing this. So I will comment this line and I will run this algorithm, for example, 1000 times. So what I expect to see now is the low cost for all the data points in our data set. So how can I check that? So I can loop through all the data points like we did before. So what we did is we wrote for I in range of length of our data. And then I assigned this index I to choose all of the data points. But there is a better, more Pythonic way to do this thing. So let me actually first finish this example. So I can now say that x, y is equal to data of I and current label is equal labels of I. And now I can print x, y, current label. And I get first two values will be x and y, and this will be the label. So let me show you a more Pythonic way to do this. So there's a function in Python called zip, where if I do the zip of data and labels, this function uses the same index to return the appropriate value from both lists, so from both data and labels. So let me show you how this works. I can say for current data point, current label in this zip of data and labels, print current data point, current label. And then this will give me first value, which will be our current data point, and the second one will be our current label. If I want to compress this even further, I can say instead of current data point, I can say in parentheses x, y. Now this will assign the first element to x, the second element to y. And now I can say print x, y, current label, and I will get the exactly same print as in this line of code, except that here I'm doing it in only 2 lines of code, and this is a more Pythonic way of working. And now I will erase this cell here and keep using this one. So what should I print here in order to check the cost? So I will print x, y, label, which is going to be current label. This gives me all of our data points. And I will print output. Well, I first need to compute the output. So output and cost, these are 2 lines of code. I will copy them and paste them here. So output will be this value here. So let's see. As you can see, outputs kind of differ from the label. So let's see what the cost is for each of these data examples. And now let's put the cost here. Cost is going to be equal to, well, this thing here. Now I can see that for some data points, the cost is kind of getting smaller after these 1000 iterations, but for some it is not. For example, for the first data point, cost is relatively high. Well, you might think this will probably improve if you just do more iterations. So let's do more iterations. Let's do 5000 iterations. And now check the cost. Again, as you can see, cost for some data points is relatively low. Yeah, so 0.64 is not really close to 1, but it is better than the first data point. The first data point should be 1, but it's actually negative. Okay, it's not working. Let's try to do more iterations. Let's do 50,000 iterations. This should fix it, no? So even after 50,000 iterations, as you can see, cost of some of the data points is getting lower, but we have reached a certain limit. we cannot improve the first data point. And also, this data point somehow is still far from 1. So what is the problem? What am I missing here? What is not working? So this is the scenario that we have faced while trying to minimize the cost for all the data points at the same time. What happens is we have a very large output space here, which is the whole number line, yeah, all of the real numbers. But we are restricting our range of valid outputs to a very, very small portion of this output space, so only around points -1 and +1. So a network which only has 3 variables, which are 2 weights, W1 and W2, and a single bias B, cannot make all of these 6 data points fit within this tiny range, yeah? So you practically have 6 equations with 3 unknowns, and you're trying to get the correct result for all 6 equations, and sometimes that is impossible. Let me give you an example of what am I exactly talking about here. So this is our formula for the mean squared error. So I take the label, and I subtract the output, and I square it. This way I get the cost for a single data point, which I want to minimize, so I want to make it as close to 0 as possible, yeah? And the output here, what is the output? Well, output is W1 times X plus W2 times Y plus B. I'm going to ask you a couple of questions here. So if we think about this expression as an equation, what would be the parameters? So why would I say think about this expression as an equation? Well, if I'm trying to practically make label minus output squared as close to 0 as possible, then from a perspective of equation, what I'm actually asking is when is label minus output squared actually equal to 0? Yeah. So if I make this into an equation, what would be the parameters of this equation? Well, the parameters would actually come from our data points. So a label would be a parameter +1, X would be a parameter 0, and Y would be a parameter 0.7. Well, if that's the case, then which elements here are the variables? Well, the variables here are our weights and biases, so W1, W2, and B. And finally, how many equations do we have here, if you look from that point of view? Well, we have as many equations as we have data points. So since we have 6 data points, we have 6 equations. So what we have is 6 equations with 3 unknowns. So if you know your algebra, then you know that this will be an overdetermined system of equations, and such system will usually be inconsistent. Well, if you're not really familiar what I just told you means, then let me give you a much simpler example of an overdetermined system of equations. So let's first consider a simple equation, 3x plus 5 equals 11. So what it is asking is 3 times what number plus 5 gives us 11. And this is a very easy equation to solve, and its solution is x equals 2. So if x equals 2, 3 times 2 plus 5 is 6 plus 5 equals to 11. So this is the one and only correct solution for this equation. But what happens if I introduce another equation with the same variable x? So now we have 3x plus 5 equals 11 and 2x plus 4 equals 7. So what does it mean that this is a system of equations? It means that we are trying to find the right answer for both of these cases, not only for one. So what is happening here? If I try to solve the first one, then the answer will be x equals to 2. And if I plug this solution to both of them, you will see that in the first one, I will get that 11 equals 11, which means that this solution is right, it's consistent. And on the other one, I get 8 equals to 7. So 8 clearly is not equal to 7, so which means that this is not a correct solution for the second equation, but it is the correct solution for the first one. Well, now if I try to solve the second equation first, I get that the right solution is that x equals to 1.5. So if I plug 1.5 to the second equation, I get 7 equals 7, which is correct. But when I plug this into the first equation, I get 9.5 equals 11, which is clearly not correct. So as you can see, I cannot satisfy both of these equations at the same time. As a system, they are inconsistent. So what our neural network, or our neuron in this case, will try to do is try to somehow satisfy both of them. It will try to interpolate values to satisfy both of these conditions up to a certain extent. So what it will probably try to do is to fit x somewhere between 1.5 and 2, such that when you plug this value, it will be relatively close to satisfy the first condition, and it will be relatively close to satisfy the second condition. But none of them will actually be correct. So for some values, and for some number of equations and unknowns, some values will be close enough to their targets, but some other numbers will not be. So by trying to get as close as possible to your target, some numbers will simply not be able to go there. So if we really try to make each point go as close as possible to its target, the whole system will become relatively inconsistent and some points will simply not be able to do that. So we need a better solution. Well, then you might ask me, how come when you use this optimization strategy, you were able to use a single neuron and correctly classify the points? How come this example that you said it was not as sophisticated worked and our current example is not working? Well, let me show you why. So what was our last example about? So we had two labels, +1 and -1. And if the red point was larger than -1, we said this is incorrect. We need to minimize the function for this value. And we did not really say how much we should minimize it. The only important thing was minimize, so push it to be less than -1. On the other side, if we had a blue point, which was smaller than +1, we decided that this was a wrong classification and we just pushed it towards higher value. So we just maximize it. We didn't say how much we should maximize, we just said push it so that it eventually comes larger than +1. So what does this tell us? Well, in this case, we have a very large ranges of correct outputs. Our correct solutions use almost all of the output space. So the only range that doesn't work is between -1 and +1. All of the other ranges correspond to correct solutions. So we cannot represent this case in terms of equations. If we want to represent it mathematically, we would represent it in terms of inequalities. Yeah? But what is the drawback of this strategy? Well, it is that we do not have the actual measure of the mismatch between the output and the label. Therefore, we do not know how much we should push certain value towards +1 or towards -1. On the other side, with mean square error, for each point we do have the exact measure of how far it is from its target or from its label. But what we lose is we lose this range of valid outputs. Yeah? So we are forced to somehow implement this range in an artificial way. So what you might be asking is there a way to actually combine these two optimization strategies so that you can still use mean squared error, but still have a range of valid outputs? And the answer is yes. So I call this strategy a probabilistic optimization strategy, and later I will explain why do I call it this way. So what do we have? So we have our neuron, as we had it before, and on the bottom we have a number line representing neuron's output. So the black point that you see indicate that our output can take the whole output space. So the output of this function can be any real number. Yeah? Well, now let's add the sigmoid activation to our neuron. Yeah? So we add it after the sum. As you remember, this is the sigmoid function, and one of its main characteristics is that its range is only from 0 to 1. So what it does, it squishes its inputs. Its input can be any real number, but the sigmoid will squish it to a range between 0 and 1. So, since sigmoid squishes its output in this range from 0 to 1, then when we apply it to our artificial neuron's output actually gets squished in the range from 0 to 1. And now when we look at our numerical labels that we assigned to the values blue and red, we'll see that they do not longer work. So the label +1 still works, but the label -1 does not work anymore because -1 is outside of this range of our neuron. So what we need to do is we need to adjust our numerical encoding. So we will leave blue points as +1, and we will now encode red points as 0 values. So first let's make this range a little bit bigger so we can see better what's going on. Well, now all the outputs of our neuron will be actually in this restricted range from 0 to 1. They cannot go beyond it. And now since our output space is a closed range, we can further split it to two ranges, one corresponding to red points and one corresponding to blue points. And now let's see what happens when we plug a data point to our neuron. So this particular point, since it is bigger than 0.5, we can declare that this is a blue point. Let's now choose another point and compute the neuron's output. So for this data point, the output of the sigmoid function will be close to 2. And since this value is on the left side of our range, so the output is smaller than 0.5, we declare that this is a red point. For each output of our artificial neuron, our point will either be a red point belonging to a range between 0 and 0.5, or being a blue point corresponding to the range from 0.5 to +1. So the value 0.5 will be the boundary between points belonging to different classes. And now you might be wondering, why do I call this a probabilistic optimization strategy? Well, this has to do with this range from 0 to 1, and how can we actually give meanings to our point according to this range that they take. What would then the label +1 mean in this context? Well, the label +1 would mean that the probability that the point is blue is equal to 1, or 100%. So label +1 means this point is 100% blue. So then what would the label 0 mean in this context? Well, the label 0 would mean that the probability that this point is blue is 0%, or 0 means this point is 0% blue. So these are the two extreme values of our range. These are our labels. But what happens when the neuron actually outputs a number which is, for example, 0.73? What would that number mean in this context? Well, this number would mean that there is a 73% probability that the corresponding point is actually blue. What it also means is that there is a 27% probability that the point is red, because the total probability is always going to be equal to 1, or 100%. So if there is 73% probability that it is blue, this automatically means that there is a 27% probability that this point is red. And what we choose actually, when we want to determine is our point actually blue or red, we choose the higher probability. In this case, higher probability is that the point is blue, therefore we conclude our point is blue. And this is how we can implement ranges into our mean squared error cost function. If we now look at our data points with textual labels blue and red, let's see how we can interpret this label probabilistically. So if the label is blue, what we can ask is, what is the probability that this label equals blue? Well, in this case, since the label is blue, the probability is 1, or 100%. On the other side, for the next point, when we ask, what is the probability that this label is blue? Well, since this label is actually red, there is 0% probability that this label is blue. So the value will be 0. In the next case, the probability that this is blue will be again 1. In the next case, the probability that this is a blue label will be 0. The same for the next case. And finally, the last point, there is a 100% probability that this point is blue. So if we numerically encode our textual data points in this manner, then they correspond very well with the outputs of our artificial neuron with the sigmoid activation. So now we are back in the exercise 7, and we are currently looking at the task number 3, which says implement the following neural network architecture and minimize the cost for all the data points. So let's see how does this differ from this one. Well, as you can see, in our previous task number 1, we do not have an activation function. Yeah? So therefore, we were not able to adequately implement the cost function to predict blue or red points. But in this example here, we do have a sigmoid function, so we should be able to do that. Well, before we actually start implementing our third task, we need to remember what we said about the labels. Since we now have a sigmoid function, the output of our network will be restricted between 0 and 1. Therefore, it makes sense only to choose our labels accordingly to this range. Therefore, we need to decide that some labels, for example, blue, will be equal to 0 or 1, and red will be equal to 0 or 1. Well, let's see what we can do. So far, we matched the blue to be equal to +1, so let's keep doing that. And the label -1, we will now change it to 0. So we will leave 1 as 1, and we will change -1s to 0s. So I will just first copy and paste the algorithm that we already developed. I will take this one. So now let's see, what do we need to change? We initialize the weights and biases. This is fine. Now we're going to run this for a number of iterations. Let's first start with very few iterations. So we are randomly choosing a point, that is fine, and label. and now we are computing the output. Well, this is where things change. Now we have a sigmoid activation after the sum, so O is now corresponds to this sum here. We will call it sum. Yeah. Well, sum is a reserved word in Python, so we cannot use sum. I will use sum with two m's, just to make sure that we do not overwrite the function which already exists. So we'll call it sum. And now we need to implement the sigmoid. So let's do that. So def sigmoid of x, this will be equal to 1 over 1 plus exponential function of negative x. Okay, this works. Let me just test if the function works. Sigmoid. You can always test if this function works by checking what is the sigmoid of the value 0. So sigmoid of 0 should be 0.5, and it is 0.5, so it works. Okay, now the sum is this weighted sum here, and now to compute the output, which I will call O, output will be equal to sigmoid of this sum. Well, then what would be the cost function? Well, cost function remains the same. It is equal to current label minus O. So current label we defined here, and the O is the output which we just defined here. It is the sigmoid of the sum. Okay, what would be the derivative of the cost in terms of output? Well, this does not change. So it is equal to negative 2 times current label minus O. So what does change? Well, what changes is now we have an additional step here. We need to compute the derivative of the output in terms of this sum here. So we need an additional step. And what is this thing? Well, it is just a sigmoid function. So the derivative of the sigmoid function is the output of the sigmoid function times 1 minus the output of sigmoid function. So it's going to be output times 1 minus output. So I will call this the sum. So the sum is equal to output times 1 minus output. Well, what I just wrote, this actually is the derivative of the output in terms of the sum, but it would be better if by this sum we meant the derivative of the total cost in terms of the sum. Yeah? So how do we do that? Well, we just have the derivative of the output in terms of the sum times derivative of the cost in terms of the output. So we are just applying chain rule. So this goes times derivative of the output. Okay, and what we are left to do? So we need to compute the derivative of the sum in terms of W1, W2, and B. And this stays the same. Derivative of the sum in terms of W will be X, in terms of the W2 will be Y, and in terms of B will be 1. Yeah, so it's the only thing that changes here is DO. So since now we have an additional step, this will not longer be valid. So it's not DO anymore, but the sum times X, the sum times Y, and the sum. So this should be it. Let's try to run it. No errors, okay. And now to evaluate how well it is doing, I will just copy this line from here, and I will need to edit it a little bit. So what I'm doing here, I'm iterating to all the data points. I'm computing the output. Okay, output is not correct. I need to compute the sigmoid of the output. Sigmoid of this sum. This will be the output. Yeah. And now the cost will be the current label minus this output squared. So the final thing that we need to do is we need to decide, according to this output of our network, whether the point is a blue point or a red point. And we remember how we did this. If the output of our network or of our neuron is greater or equal to 0.5, we decide this is a blue point. And if it is less than 0.5, we decide it is a red point. So how we can implement this? Well, we can say prediction equals 1, which corresponds to a blue point, if the output is greater or equal than 0.5. Otherwise, the prediction is that it's a red point. So if it is not a blue point, it is a red point. Else 0. So now let's change this print statement. So we have what is the current label, and we can keep the output. And now instead of costs, I will first ask, what is the prediction? Now I get what is the label and what is the actual output, and according to that, what is the prediction. But we can also ask, is this prediction actually correct or not? So how do we do that? We can ask, is this correct? And ask, so for a prediction to be correct, our output needs to match the prediction. So O, which is the output, needs to be the same as prediction. Let's now run this. Actually, I made a mistake. I need to ask whether the current label matches the prediction. As you can see, now we have more true cases. So the label is 1 and the output is greater than 0.5, therefore the prediction is 1. Therefore, this prediction is correct. Yeah, and the cost is very small. As you can see, cost for all of these examples is kind of small. Let's now do 5,000 iterations. As you can see, now all the predictions are correct. So correct equals true. As you can see, the cost is going down for all of these data points. And as the cost is getting less and less, our predictions are getting more and more correct. And now we have 100% accuracy in predicting our label. Now, after the implementation, there are still a couple of drawbacks that we need to address. So first of all, we know that our network is improving, but we do not know how much. So we know what is the cost for a single data point, but it would be better if we had some kind of a global measure of improvement. And the second thing to consider is that this kind of approach is very computationally expensive because we are computing partial derivatives for all the weights and biases after a single data point. So right now, since we only have 6 data points, this is not a big issue, but once we have tens of thousands of data points, that is going to be a problem. So we need to see how we can address this potential deadlock. These two issues and some others we will address next week. That will be all for today. I hope you enjoyed it, that you learned something. Stay at home and see you next week. Bye.